Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to discuss another important topic in this lecture. The topic is complex numbers. We need the idea of complex numbers to discuss the superposition of simple harmonic motions. So I will develop this idea. You may know it. If you know it, this lecture will be helpful for refreshing your ideas. So it will help us to move forward. You know the idea of quadratic equation. The general solution of the quadratic equation, which is az square plus bz plus c equal to 0. I name it first. So this is the quadratic equation. Z is the variable, A, B, C are constants. So this is the quadratic equation for unknown Z. And its solution is given by the quadratic formula. You know this. What is the quadratic formula? Z is equal to minus b plus minus square root of b square minus 4ac whole divided by 2a. I name it second. Z is equal to minus b plus minus square root of b square minus 4ac divided by 2a. And the thing in the square root, b square minus 4ac, is called determinant, denoted by d. It is called it is called discriminant. So if we have a general quadratic equation for unknown z given by equation 1, its solution is given by this quadratic formula. Let me use another color. Z equal to minus b plus minus square root of b square minus 4ac whole divided by 2a. I name it second. Now I am saying that if the discriminant, by discriminant I mean the thing in the square root b square minus 4ac, if this discriminant is negative, we must take the square root of a negative number in order to find z. I repeat, if the discriminant d equal to b square minus 4ac is negative, we must take the square root of a negative number in order to find z. Since only non-negative numbers have real square roots, it is impossible to use equation 2 when d is negative unless we introduce a new kind of number called an imaginary number. Let me write it. Since only non-negative numbers have real square roots, it is impossible to use equation 2, this equation 2 quadratic formula, when our discriminant d is negative, that is less than 0, unless we introduce a new kind of number called an imaginary number. Now we use the symbol iota equal to square root of -1 with the understanding that iota square is equal to -1, right? So we use the symbol iota for square root -1 with the understanding that iota square is -1. Then square root of -16 can be written as 4 iota. The square root of -1 is iota and square root of 16 is 4. So it is 4 iota. Similarly, square root of -3 can be written as iota square root of 3, right? What about iota cube? Iota cube is just minus iota because iota square is -1. So it is iota square into iota, that is minus iota, right? Now these numbers, square root of -16, square root of -3, or iota cube, or numbers like them, are called imaginary numbers. So these are imaginary numbers. But iota square equal to -1 square root of -2 into square root of -8, which is iota into square root of 2 multiplied by iota into square root of 8, which is minus 4, or iota raised power 4n is equal to 1 are real numbers. Are real numbers. I repeat, when we introduce this idea of imaginary numbers, then we say the numbers like minus square root of minus 16, square root of minus 3, or iota cube are imaginary numbers, but numbers like iota square equal to minus 1, square root of minus 2 times square root of minus 8, which can be written as iota times square root of 2 times iota times square root of 8, which is 4 minus 4, or iota raised power 4n is equal to 1. Such numbers are real numbers, right? Now in equation 2, we also need combinations of real and imaginary numbers. Let me give you an example. The solution of this quadratic equation, z square minus 2z plus 2 equal to 0 is z equal to 2 plus minus square root of 4 minus 8 over 2, which is 2 plus minus square root of minus 4 over 2, which is 1 plus minus iota. I repeat, the solution of this quadratic equation in z square minus 2z plus 2 equal to 0 is z equal to 2 plus minus square root of 4 minus 8 divided by 2, which is 2 plus minus square root of minus 4 divided by 2, which is 1 plus minus iota, right? It is 1 plus minus iota. Let me encircle it. You can check it using this quadratic formula. So check it at home, right? Now we use the term complex number to mean any one of the whole set of numbers, real, imaginary, or combinations of the two, like 1 plus minus iota, right? I repeat, we use the term complex number to mean any one of the whole set of numbers, real, imaginary, or combinations of the two, like 1 plus minus iota. Thus, iota plus 5, 17 iota, 4, 3 plus iota root 5 are examples of complex numbers, right? 1 plus iota plus 5, 17 iota, 4, 3 plus iota square root of 5 are all examples of complex numbers. When people first considered taking square roots of negative numbers, they felt very uneasy about the problem. They thought that such numbers could not have any meaning or any connection with reality, hence the term imaginary, right? So let us move to next idea, real and imaginary parts of a complex number. Let me underline it. Real and imaginary parts of a complex number. Now, a complex number such as 5 plus 3 iota is the sum of two terms. 5 is one term, 3 iota is another term. The real term, the term not containing I, we use another color here. So this term is called real term. The term which does not contain I, right, is the real part of this complex number. So 5 is called the real part of this complex number 5 plus 3 iota, right? And the coefficient of our iota in the other term, that is this plus 3, coefficient of iota in the other term is called imaginary part of the complex number 5 plus 3 iota, right? So 5 is real part of this complex number, and the coefficient of iota, which is plus 3, is the imaginary part of this complex number, right? Notice carefully that the imaginary part of a complex number is not imaginary. Plus 3 is a real number. So let me write it. The imaginary part of a complex number is not imaginary, right? Now, either the real part or the imaginary part of a complex number may be 0. If the real part is 0, the complex number is called imaginary, or for emphasis, pure imaginary, right? The 0 real part is usually omitted. Thus, 0 plus 5 iota is written just as 5 iota, right? So 5 iota is pure imaginary. Now, if the imaginary part of a complex number is 0, the number is real. We write 7 plus 0 iota as just 7. So complex numbers then include both real numbers and pure imaginary numbers as special cases, right? Now in algebra, a complex number is ordinarily written as a sum like 5 plus 3 iota. There is another way which is very useful of thinking of a complex number, right? As we have said, every complex number has a real part and an imaginary part, either of which may be 0. These are two real numbers, and we could, if we like it, agree to write 5 plus 3 iota as 5 comma 3, right? Now, any complex number could be written this way as a pair of real numbers, the real part first and then the imaginary part, which you must remember is real. This would not be a very convenient form for computation, but it suggests a very useful geometrical representation of a complex number, which we are going to now discuss. So our next idea is the complex plane. Let me draw the figure. Let me use another color here. In figure 1. Now, in analytic geometry, we plot the point 5 comma 3 as shown in figure 1. This point represents 5 comma 3. As we have seen, the symbol 5 comma 3 could also mean the complex number 5 plus 3 iota, right? So the point 5 comma 3 may then be labeled either 5 comma 3 or 5 plus 3 iota. Similarly, any complex number x plus iota y, x and y being real, can be represented by a point x comma y in the xy plane, as we have shown this. This point here is x distance from the origin along x-axis and y distance from the y-axis, from y distance along y-axis from the origin. So this point represents x comma y, or the complex number x plus iota y. Also, any point xy in the xy plane, as we have said it, can be labeled as x plus iota y as well as x comma y. Now, when the point x comma y is represented, is used to represent the complex number x plus iota y, then this xy plane is called the complex plane. I repeat, when the xy plane is used in this way to plot complex numbers, it is called complex plane. So we call this complex plane. It is also sometimes called, this diagram is also sometimes called an Argand diagram, right? The x-axis is called the real axis. So x-axis is called real axis, and the y-axis is called the imaginary axis, right? And you need to note, however, that we plot y, not iota y, right? Now, when a complex number is written in the form x plus iota y, we say that it is in rectangular form. Rectangular form, because x and y are the rectangular coordinates of the point representing the number in the complex plane. Now, in analytic geometry, we can locate a point by giving its polar coordinates r comma theta instead of its rectangular coordinates x comma y, right? As shown in this figure, we draw the figure. I name it figure 2. This was my figure 1. So this is x-axis, this is y-axis, and this is some point P with rectangular coordinates x comma y. If it is r distance from the origin, and this angle is theta, then we know this is x coordinate, and this distance is y coordinate of point P. So there is a corresponding way to write any complex number. In figure 2, we see x is r cos theta and y is r sin theta. Then we have x plus iota y. Instead of x, we will write r cos theta plus iota r sin theta. I can take r common and write it this way: cos theta plus iota sin theta, right? Now this expression, let me name it x plus iota y is equal to r times cos theta plus iota sin theta, is called the polar form of the complex number. Polar form of the complex number, right? So when we write the complex number in this form, x plus iota y, it is rectangular form. If we write it in terms of this, r times cos theta plus iota sin theta, it is called the polar form of the expression. Now, this combination cos theta plus iota sin theta is equal to e raised power iota theta. So a convenient way to write polar form of a complex number is, you can write x plus iota y equal to r cos theta plus iota sin theta, which can be written as r e raised power iota theta. We made use of this formula: cos theta plus iota sin theta is equal to e raised power iota theta, right? The polar form r e raised power iota theta is of a complex number is often simpler to use than the rectangular form. Now I will discuss an example with you. Let me draw the figure. This is my y. This is my x. I'll complete the figure first, then I will explain it. Let me use another color. This thing will be pi by 3 radians. I'm using another color. Let me use another color. Let me name this figure 3. Let me check it. R sine theta 2 is 2 sine pi by 3, which is root 3. X is r cos theta, which is 2 cos pi by 3, which is 1. So let me discuss this example. Now in this figure 3, the point, we have selected a point A, which is labeled as x comma y, which is 1 square root of 3, because this distance, the distance of this point from the origin, which is r, is 2 units, and this line is making angle pi by 3 radians with the x-axis as shown. So when we see this x coordinate of this point, it will be r cos theta, which is 2 cos pi by 3, which is 1, right? So its x coordinate is 1. So therefore I can label this point A as 1. 1 denotes x. Then what about its y coordinate, which is r sine theta? R is 2, then angle is pi by 3 radian, so it is 2 sine pi by 3, which is square root of 3. So its y coordinate is square root of 3. Its x is 1, as we have calculated it. You can check it. So this point A can be labeled as x comma y, which is 1 comma square root of 3, or we can label it as 1 plus iota square root of 3. If we write in terms of the polar coordinates r and theta, r is 2, theta is pi by 3, so we can write it 2 comma pi by 3, or we can write it this way, which we have discussed, that we can write in polar form any complex number as r cos theta plus iota sine theta. So I can write it r, which is 2 cos theta, theta is pi by 3, plus iota sine theta, which is pi by 3, or you can write it r e raised by iota theta, which is 2 e raised per iota pi by 3, right? So we have uh, uh, written this point A, we have labeled this point using rectangular coordinates as well as the polar coordinates. So you can label it either at 1 comma square root of 3 or in complex notation, or you can make use of the polar coordinates and write it in terms of complex notation, right? So I will end this lecture. I will summarize the lecture. So we started with the quadratic equation in unknown z, and we said its solution is given by this quadratic formula equation 2. Then we said if its discriminant, the thing in the square root b square minus 4ac, is negative, then we need to introduce a new kind of number called imaginary number, so that this equation 2 can give us solutions to equation 1, because only non-negative numbers have real square roots. So we introduced the iota, which is square root of -1, with the understanding that iota square is -1. Then we said square root of -16, square root of -3, or iota cube are imaginary numbers, and numbers like iota square, square root of 2 times square root of -8, or iota raised power 4n, which is 1, are real numbers. Then we gave this example. We said the solution of this quadratic equation is 1 plus minus iota. Then we said a complex number is in general written as a sum of two terms like 5 plus 3 iota. The first term, which is the real term, is called the real part of the complex number, and the coefficient of iota, which in this case is plus 3, is called the imaginary part of this complex number 5 plus 3 iota. Then we noted that imaginary part of a complex number is not imaginary, and we said if the real part of a complex number is 0, then it is called pure imaginary. If its imaginary part is 0, then it is real, like 7 plus 0 iota is written just as 7. Then we said we can write 5 plus 3 iota as 5 comma 3. Then we talked about the complex plane. We said we can represent 5 plus 3 iota as 5, 3, as shown in this figure. And when we use xy plane this way to represent complex numbers by points in this xy plane, this plane then is called complex plane. X-axis is called real axis, y-axis is called imaginary axis, and this diagram is called Argand diagram. Then we said that complex number can be written in this way. This form of writing a complex number is called rectangular form, and this form, when we write complex number in this way, r cos theta plus iota sine theta, are making use of polar coordinates of point P, or we make use of this formula cos theta plus iota sine theta is per iota theta. This form is called rectangular form. Then we discuss this example. So this is all for today. Go through all the lectures. Don't waste your time, and don't forget to like, share, and subscribe my channel. Thank you. God bless you. Assalamu alaikum.